So happy Monday, everyone. Happy dark, cold, rainy Monday morning. So this is the revision lecture. And so we're going to talk about the material today and test preparation and all that stuff. Are there any questions before we start talking about that? So I have some news. So the test is more difficult this year than past years. That's some news.
Then should I follow the past paper examination or not?
Yes, you should study the past papers, definitely. But this one, keeping in mind that this one's more difficult than the past ones. Yeah.
Good sense.
In the past papers, you're given a lot to start with. Like, here's a parallel coordinates visualization. You're not given much this time. It would, rather than being given a parallel coordinates visualization, you might have to construct a parallel. You're given a lot of stuff in previous exams. Like, here's something, now build on it. This time it's, okay, I want something from you, and then build on it too, if you know what I mean. So it's not as easy as the previous exams. There are some reasons for that. One is that the previous exam scores were very, very high. You know, they were like always in the 70s. Not always, but they were very high. So I thought it was too easy. Some students were telling me like, oh, it only took me a half an hour and I just walked right out of there, stuff like that.
Give me the names.
Secondly, I think this is a smart class. I think this class is smarter than the previous years. Thirdly, and maybe most interestingly, is you're the most well-equipped class to prepare for this exam. You have material that nobody else has ever had, and that's true for all of your modules. So all of the lectures are here on the DataViz YouTube channel. They're all here. So if you're not sure about something, there's Introduction Part 1, and so on. If you're not sure about something, you can just access the lectures and revisit the topic, which is very unusual. Has anybody experienced that before in some other class? I've never experienced that before. I've never in my whole life. And maybe I never will, because I'm not studying for a test anymore. So that's all that material. There are 2 lectures missing. One is the introductory FlowViz lecture, that something went wrong with the recording. And the other one is the stream surface construction lecture. Something went wrong with that recording too. And I still have 2 more to upload. The streak surface construction, which does overlap with the stream surface construction. It's more difficult in today's. Any comments or questions about that? I know as a student that I didn't understand a lot of things, and I guess it's still true, the first time I heard them or saw them. But I did understand them the second time I heard them or saw them. I know that I experienced that a lot. I can tell some very geeky stories about that. If anybody's interested. I don't know. For some reason, a story I always remember, this is really geeky, so please forgive me. But when I was in high school, I remember we had the option of taking calculus in our final year of high school, and calculus had a reputation for being difficult. But I knew I had to learn calculus if I wanted to study, for example, if I wanted to study physics in university. So I thought, okay, I'm gonna take it as a senior in high school. I can see some people find the story very exciting. I'm gonna take it as a senior in high school, and then so when I don't understand some things, I'll see them again as a first year at university, and I'll catch them the second time. And that's exactly what happens, like exactly. So I remember taking it in high school, doing okay until we got to integration. And then when we got to integration, I didn't understand it. I got totally lost. And then when I took it again as a first year university student, when the teacher said, oh, we're gonna start integration today, I was like, oh, this is the part I didn't get. I need to pay attention, and I got it the second time. So you guys have a new kind of luxury at your disposal. Here's another big hint. So last year, students were sending me questions about the exam. And rather than try to write some email that didn't make any sense to just one single student, I would answer their questions in my office using a blackboard, for example. And then I would put it on YouTube. Plus I was traveling, right? I was traveling to different places like Texas and Florida and all that stuff. And so there are these are questions from students last year about test preparation. And some of the questions I thought, oh, these would make good test questions. So that's another hint, right? Some of the questions are very good. So basically, here's my spreadsheet of, oh, that's the wrong one actually. I want to use 16, save as. Those are the notes, and I'm going to go through the lectures. I'm going to try to go through all of them and just make note of the terms that you need to learn and understand. Choose a different together. This is. Let's try that again. Okay, well, I guess I just save it as 15. Will it let me save it as 15? Okay, I can at least save it as 15. That's good. So we'll look at the previous lectures. I'll tell you what terms you need to know and what algorithms you need to know, and you can ask me questions. Say, Bob, like, can you tell us about that term again? I didn't understand it the first time. But if nobody interrupts me or asks any questions, I'm just going to cruise right through. Right? So let's look at the first lecture. So we went over this knowledge pipeline, right? And there it is in my notes, pattern of knowledge evolution, the big data story, the background on visualization, some examples, right? Goals, goals, sometimes I might put something in bold, right? Very, very important. Present and accelerate. We had our subfields, and then we had the visualization pipeline, right? The visualization pipeline. I'm going to put that one in bold. 4 stages, right? So that's the first lecture, right? Pretty simple. Right? Anybody have questions about the first one? And you'll see in my amazing spreadsheet, which I do upload to Blackboard, by the way, to the Blackboard module for everybody to get a copy. I have these different columns. One's called introductory topics, information visualization, volume visualization, flow visualization, and I have a special column for algorithms, right? So these are kind of terminology, and this is like recipes to get things done. I happen to like algorithms, so that's why they have their own special column. So, intro 2. This is all about data, right? So, dimensionality of data is a big topic, right? Data dimensionality. 1D, 2D, 2.5D, 3D, ND, data characteristics, right, is a big topic. And visualization dimensionality is another big topic. So we have data dimensionality and visualization dimensionality, and they're not the same, or not always the same. And we talked about color and colors, the Mach band effect. Yep.
What kind of questions would we have after the updated ones? Is it gonna be like
About colors.
the algorithms?
The algorithms. So for algorithms, you could get a question, and you'll see this on previous tests. Please outline and describe and illustrate the 8 steps of the Marching Cubes algorithm, for example. So that's a typical kind of test question. So you'll have to remember some algorithms. Also, on this year's test, there's a lot of drawing. So feel free to bring pencils and erasers and different colored pencils and erasers, because you're asked to draw things a lot. Yeah, illustrate. I'll be looking carefully at your illustrations to see if you know what's happening. Right? For example, can you illustrate how divergence is handled in the stream surface construction algorithm? So you draw a little diagram of 2 quads splitting, for example. Or in the Marching Cubes algorithm, you draw the first step is to examine a cube. So you might draw a cube with the vertices labeled, like this is the first vertex. Sounds like fun, doesn't it? It's
Not fun.
no. Would you rather just write stuff though? I think for the Chinese this should be especially fun. Because would you rather try to construct English sentences for all of your, rely purely on English sentences in text? Or would you rather rely on beautiful drawings that convey your understanding? Drawings are not going to, they don't require the complexity of the natural language as much, right?
You're right if I could understand
But
the
we've got
drawing.
good memories.
Say it again.
It would be great if I'm sure like I'm understanding the concept very well.
Mm-hmm.
But if I don't understand it, I could lose it. With writing, I can write, I can just
Yep.
try.
You can use writing on the test. It's fine. It's fine. If it asks you for an illustration and I notice you've tried to avoid illustrating it, then I know, oh, there's something wrong, or there might be something wrong.
But would you accept like if I write something instead of
No, with the diagram, you can clarify your imagination or your answer will be more strong.
So let me ask you this. Would you rather describe a cube using text, or would you rather just draw a cube?
rather do both?
Both.
Both. Okay, that's fine.
Explanation
That's
and-
fine. Yeah.
That's why I'm asking if it's okay to write like
Yes, definitely it's okay. It's going to ask for illustrations and descriptions.
I think it should be optional. If someone wants to know something,
they should.
yeah, I don't want to interfere with other people. Because
Mhm. I mean, everything is optional, right? Nobody's going to force you to do anything. You'll never find the sentence like, you must do this on tests. Feel free to interrupt with any other questions anytime. The mock band effect, everybody thought that was cool. Remember that? Now you notice that. There's not much about, I thought you were going to ask about color. Like, what could there be about color on the test? There aren't generally many questions about color on the tests. It's not really a central focus. Having said that, some students bring colored pens and pencils, which I do think can help sometimes. Yeah. So that's the introductory material. I see. Who is the demo? Oh, actually, yep. Uh-huh. So we talk in this about the two big topics are hierarchical data visualization and focus and context visualization. So we first clarified some terminology about the data dimensions again, and we went over some important goals, special challenges, and it's all about big data sets, big complicated data sets, right? How to deal with big complicated data sets, and then we went into some examples, and then we talked about hierarchical visualization techniques, so conventional trees, right? This is a hierarchical text-based visualization that we see on a daily basis. We talked about the limitations of the conventional tree hierarchical visualizations, Venn diagrams we talked about briefly, and then tree maps, which are sort of an extension or an improvement over Venn diagrams. We talked about the first so-called algorithm, which was the tree map construction. Right, so we have our abstract versus spatial data, information versus scientific visualization, hierarchical trees. This can be like conventional trees, conventional methods, Venn diagram, tree maps, tree map. We talked a little bit about the tree map node size, and that's the first algorithm over here, the tree map construction. That was our first. Then we looked at the demo, right? The amazing demo. I use this program all the time, by the way, to find out where my disk space disappeared to. We looked at one a live demo from the web. This is the visualization of the stock market. We looked at combining tree maps with scientific visualization briefly. Here's a word tree example. Right, so we have tree map. I didn't put word tree in there. I could put that in there actually. Insert cell, shift cells down, word tree. This is actually an interactive word tree. They're all interactive actually. And just for fun, I can insert a space just to see, so you can separate these two lectures. So then there's the big lecture, InfoVis 2, big lecture. I think I should juggle this material a little bit so this it's not so much as not crammed into this one. So in this one, we're talking about graphs, n-dimensional data, icons, and interaction techniques. It's a lot of material in this one. So we talked a little bit about graphs, and we know that that could be its own module itself. Oh, I see. Graphs, goals, optimizations, challenges. See, you can see how the topics go further down in this column. Graphs, goals, optimizations, and challenges. Famous graphs. The advantage of graphs. Graph layout algorithms. We didn't actually go over the steps of any graph layout algorithms, by the way. So graph layout algorithms is not in this list of algorithms over here.
So it's quite difficult, the graph algorithm what you have shown. Is it necessary to memorize that?
No, there's not going to be a test question that says, please provide a graph algorithm. There won't be. There are millions of them, by the way. Millions. It would be interesting. I don't know how this graph algorithm works, but it would be lots of fun to find out. Could be a good coursework. What?
Test.
This is the part of you, as you explained, I remember for the software engineering.
That's right. This is from software engineering. This example. Yes. Good memory. Good memory. It's from a package called Doxygen. Is anybody taking the software engineering module in here? So you'll see Doxygen in the software engineering principles module in our software engineering modules. And there were some more real-world examples. We talked about graphs, lots about graphs, and we went into this case study. So graph examples, orthogonal flow, higher order, case study, interaction. So this was some specialized topic in graphs. This is just one of millions of examples. I just thought it would be nice to pick out one example of some kind of advanced topic in graphs, just so you can get some exposure to that. N-dimensional data. So these are all n-dimensional or multivariate or high-dimensional visualization techniques. And there are a number of them here. right? So a scatter plot matrix, right? An interactive scatter plot matrix, the 3D scatter plot, stacked bar chart here, stacked graph, matrix chart, and then glyphs. We started to talk about glyphs, Chernoff faces, star glyphs, Chernoff faces. I'll give you a hint, Chernoff faces are not on the test. They're famous and all that stuff, but I don't think that they're very, very successful as a visualization technique. Star glyphs, vector glyphs, range glyphs, hybrid glyphs, rugby glyphs. We watched the rugby video. Those are detailed, lots of detail about the rugby glyphs. And we looked at the rugby visualization software. Then we talked about parallel coordinates, interaction techniques with parallel coordinates like brushing, right? Hierarchical parallel coordinates for big data, angular histograms for big data, interaction, linking and brushing, and coordinated multiple views. And we looked at this special case study, FlowViz Pastor Marine turbine. And we also discussed briefly chord diagrams, although there were no slides on chord diagrams. But we showed a video of a chord diagram. Any questions on information visualization? I'm trying to use my psychic powers to pick up any signals right now. But questions on information visualization? I think one of the signals I'm picking up is, could chord diagrams be on the test? Is somebody thinking that? Is that a false signal? I think somebody is thinking that. The answer is yes, it's possible. It's possible. I got a signal about that. Maybe it was a false signal.
For this table or what?
This is going to be on Blackboard, yes. The last year's is already on Blackboard. Yeah. So, volume visualization, you'll notice that the topics are quite different. Volume visualization and information visualization. Big change in the way the visualizations look and the style. Are there any other InfoViz? Okay, there are 3-ish algorithms for InfoViz. There, tree map construction, parallel coordinates. I don't know if that you call that an algorithm, but it's pretty close. Yeah, I guess it's an algorithm to construct parallel coordinates. And glyph design, like, can you design a glyph that gets the following properties of a data set visualized, for example? That's not really an algorithm per se, but it's very close. It's really a process that could be called a process. And then we talked about volume visualization, what it is, where volume data comes from. sources of volume data. Talked about tetrahedron, like what it is. We used to have lectures on grid structures, like different kinds of grids, and we used to have a lecture about this, but I took it out because it's not something that's popular enough. So if you look at some old tests, you'll see questions about grids. There aren't going to be test questions about grids. Those are old. I swapped that out for some more InfoVis stuff. Volume visualization challenges, so lots of data in volume visualization, cells versus voxels. Terminology. Interpolation is very, very important. Right, I can put this in boldface. That's a very important notion or term. And actually, I could put that in the processes. Column. Interpolation. I'll call this algorithms and processes. So interpolation is important, very important. Used all the time, constantly. We looked at the conceptual volume visualization framework. Is that in our list here? Yes, conceptual volume visualization framework. Look at that. Compare with the Viz pipeline. Wow. Talk about detailed, helpful notes. That's shocking, isn't it? And then different examples of traversing. By the way, does this make more sense to everybody now? Now that we've been through it? You saw this the first time, might not have made sense, but now I hope it makes sense, this thing. Starting with measured data. This is Betty. Betty is measured data. Sally is modeling. We can represent Betty as voxels and then do volume rendering on Betty. With Sally, we can do the same thing, but with Sally, we can also extract surfaces directly, right? And so we can go from voxel space to geometric space. So using isosurfacing, we can go to voxel space with voxelization and traverse this space in lots of different ways. Actually, with Sally, what we did was we took the analytical data and we put an arrow here, and we output Sally in the sampled data format, really. And then we construct our cells. Go down this way, actually. Hopefully that makes more sense now. Right. We talked about direct versus indirect, although that's not really that important. Image order versus object order, that's more important. Slicing. We talked about. And we mentioned aliasing, anti-aliasing, very important. And that was that one. Any questions about the first Volume Viz lecture? Okay, if anybody has questions, feel free to interrupt at any time. We talked about isosurfacing. And iso contours, iso surfaces. What is an iso surface? What is an iso value? Iso surfaces and iso values, iso contours, marching cubes. Right, marching cubes is our first volume. Well, it's a volume visualization algorithm. Oh, marching squares. Where's marching cubes? Marching cubes. Actually, that's the one we want. I thought that was. So that's marching squares, and then this is marching cubes. By the way, I don't know if anybody noticed, but Bill Lawrenson watched the lecture on marching cubes that I gave for this module, and he liked it. And I asked a question about, I said, oh, I wonder how they did this, and he answered the question in the comments. I was really shocked. I had Bill Lawrenson stories. But I wondered, so they have a case table, 256 cases in the algorithm. You can look at the case table in the source code. And I wondered, how did they make that case table? Because that's a long and tedious process to get 256 cases correct, right? This cube has to be rotated 1, 2, 3, 4, and then flipped, and then rotated 4 times to get 8 more cases, right? To do that manually, and then map those configurations to these edge intersections. For me, that seemed extremely, extremely tedious, and then I wondered, oh, how did they do that? Or how that must have taken a few days or something. But he said they wrote a little program that rotated the cubes automatically and then produced the edge cases automatically. So they wrote a program to rotate this cube 90 degrees, then 180 degrees, then 270 degrees, and then flip it and do the same thing. So they did it with the help of software. And that would have to be done for, I believe, yeah, all of these cases. You'd have to rotate them all 90 degrees, 180 degrees, 270 degrees, flip them, and do the same thing. So yeah, that's an interesting process.
So what kind of questions would they have?
So a question could be like, can you outline the marching cubes algorithm? Can you recall the 8 steps, for example? It is possible to pick a step or a few steps and then go into more detail. I could ask a test question that's just consider step 7 or the case of ambiguous cases in marching cubes. What's one way to handle ambiguous cases in marching cubes?
What about the algorithm?
About the what?
The algorithm?
The algorithm. What about it?
We didn't have like.
That could be on the test. You'll see that on previous tests. Like here, please tell the marching cubes algorithm. One thing I didn't mention really is why it's such a great algorithm. And it's because it enables you to process the data one cell at a time. And this is a great property. Actually, in reality, it's 1 or 2 slices of data at the same time. So you can load in 2 slices of data from the volume, extract your surface, then release those 2 slices from memory, and load in the next slice or slices. So you can traverse the data 1 or 2 slices at a time. As opposed to loading in the entire data set, extracting the surface, and then trying to dump the data set, because most or a lot of volume data sets are too big to load all at once into memory. So the previous algorithms tried to load the entire data set into the memory at the same time, and that causes thrashing, right? If the data doesn't fit into main memory, right? You get lots, it slows down. I didn't mention that the first time. Any other questions with that? And those are the 8 steps. I mentioned that this is the most difficult one to understand. Well, it's one of the more difficult ones to understand, I would say. This happens to be, by the way, the computation of gradients. I don't know if I said that at that time. We call it a central difference. Calculate the normal in each vertex using central differences. But that's also the way we compute gradients. I don't think I said that because we hadn't talked about gradients at that point last time. Any questions about that lecture? And I would look at the papers and read the papers, by the way. So I go through the algorithms very quickly, right? Because we have a quick time. We don't have much time. But here you can read each step in detail at your own pace, right? If something didn't make sense to you, the way I explained it, you can read. And those are on Blackboard, those papers. Yep. You can download this paper from anywhere, Google Scholar as well. Okay, then we went into, I can say, sort of 8 basic steps. Ray casting, isocontours, isosurfaces. So we went into this whole idea of ray casting. We introduced the term ray casting and ray casting versus ray tracing. Ray casting functions, ray functions. It would actually be nice to put ray casting in its own cell. Ray functions, very important, right? This was a test. This has been a test question on previous tests. And we mentioned this term classification. That's not going to be on the test though, actually. Transfer functions. I hope it's in my, yes, transfer functions and compositing. 1D versus 2D transfer functions. This is a so-called 1D transfer function. We talked about gradients. Then the 2D transfer function, that's the 2D transfer function, and then the ray casting algorithm. So ray casting is one of the algorithms, right? And that's the overview of the ray casting algorithm. Step 1, step 2, step 3. So now, did we go over that? So I would have a look at this paper, by the way. That's also on Blackboard. And if you have access to this book, it would be good to look at chapter 10 of Alex Talaya's book. Any questions about that lecture? It's exciting, isn't it? I can feel the excitement. And then the shear warp algorithm. So there are 3 basic steps in the shear warp algorithm. Shear warp algorithm. So here we have 3 basic steps. Raycasting. Here we also have 3 basic steps. Right? And then we had the description of how run length encoding is used. These were questions, by the way, that students were asking on last year's test. Like one student said, oh, can you just go over the shear warp algorithm? So there it is, an explanation of the shear warp algorithm, a fast and convenient summary. And then a student asked, oh, I don't understand the run length encoding part of the shear warp algorithm. Can you explain that? So that's an old-fashioned chalk whiteboard explanation, just a whiteboard without any slides explanation. It turns out that somebody also asked, what about ray casting versus ray tracing? And I thought, oh, that's a good question. You know, I didn't talk about that very much in class. And this turns out to be quite a popular video. Like, a lot of people watch this from all over the world, actually. Yeah, so a lot of people are wondering about that question. And perspective projection, that is a good question, actually. That would be a good test question. It's quite an advanced question. It's not going to. This one is not going to be on this year's test, but it's a good question, actually. Well, like for the advanced, this questions like sort of they have the beginner level, part A, and then the intermediate level, part B, and then the advanced level, part C. Sort of. That's generally how test questions are structured here. And so this would be a good part C. It's not part C this year, but it would make a good part C. And I would have a look at that paper. You know, if I was taking this test. You definitely, the papers are not really easy reading. So you can't just read all the papers the day before the test. That's not going to work. You might have one paper per day or something like that. Or I actually split the papers up into 2 sittings, like 4 pages the first sitting, and then 4 pages the second sitting, maybe in the same day or something like that, or maybe on different days. We did not talk about the comparison at all. And shall we finish this up today? Or unless we get kicked out? Is it gonna get kicked out? So we'll just go for a few more minutes. There is another lecture at 10 o'clock. The FlowViz stuff. So the FlowViz intro stuff. What is flow visualization? The definition, challenges, different classifications, right? Origins of flow data, sources of flow data, steady versus unsteady flow, direct versus geometric FlowViz. And there's not going to be any exam question about experimental FlowViz. We went over some demos. I'm going quickly now. And we talked about arrows, arrowglyphs, using arrows and glyphs. And we talked about numerical integration. This should be actually here. Insert cells. Shift cells down. Numerical.
Is it important to the numerical integrations? Is it important for the
It was on last year's test. Yep. So it was, here's a seed point, compute the next streamline point. That was a question on last year's test.
that bit difficult?
Yeah, it is difficult actually. That's not, it's easy to make a mistake. That's why there's a special tutorial on YouTube just for that question. It's shocking, isn't it? Wow, a special tutorial on YouTube just for that question. Shocking. Like the level of service. It's a new level of service. Serious education. It's serious education here. So we went over and you can watch that lecture again, by the way. That is on YouTube, that lecture. Last year, the students didn't have the lectures on YouTube. They couldn't watch the lectures again. It's very convenient. It's very convenient. We talked about streamlines. So direct numerical integration. Streamlines, pathlines, streak lines. And then streamline placement. So that's one of the algorithms. I think they're going to get upset at me. This evenly spaced streamlines algorithm. That's there. And the last bit was stream surfaces and streak surfaces. We're about to get kicked out. So, stream ribbons we talked about. That's here. Streamline placement, stream surfaces, path surfaces, streak surfaces, quads, streamlines, stream ribbons, and stream tubes. And then we talked about how to construct stream surfaces. Right? That was the algorithm. So stream surface construction is there. And there are 3 basic steps. Anybody, that was a low attended lecture, that one. But it was a very important one for the upcoming test, actually. And then we talked about streak surfaces and streak surface construction, which is more complicated, but an extension of stream surfaces. So that's on here. T-junctions, texture-based flow viz we didn't talk about. Texture advection we didn't talk about. And feature-based flow viz we didn't talk about. Any questions? So I'm going to leave it up to, is it Elif, about the lecture on Thursday. If you tell us we should have a lecture on Thursday, then we will. If not, we won't. You'll let us know within the next 24 hours, I guess. You'll ask the master's students if they want another revision lecture, and then
We can talk, but I guess they don't want to have another lecture because we have course break.
Yep. Okay. Maybe you send me a confirmation message in the next 24 hours. You can ask. Happy Monday.